Talking about percent yield and the final thing really being energy stoichiometry. Again, as we've talked, energy stoichiometry, that's just another thing that's going to be involved with the stoichiometry that we've already been doing. And percent yields, it's really a lot like what we've been talking about with percent error. Percent yield, it describes how much product was actually made in the lab versus the amount that theoretically could be made. Now, what it's going to be is percent yield is your actual product or your actual yield, and again, lab setting, divided by your theoretical. Think of that word in theory, perfect reaction, times 100, and then like I said, add the percent sign. So again, it's a percent yield. Instead of finding the error, what we're doing is we're finding how much good we have. Percent yield, like I said, it tells you how close you were to the 100% mark. Now, you're not always going to have the perfect reaction. Reactions don't always form that perfect reaction. Experimental errors, spills, contamination often means that the amount of product made in the lab did not match that ideal amount that could have been made. Most of the times, like I said, you're going to definitely be under 100% because, again, there is that human error, misreading, parallax, things like that, that end up occurring. Unwanted chemical reactions because of contamination or stuff like that in your beakers. Theoretical yield, just like I said, in theory, the perfect thing. So it's the maximum amount of product that could be formed from given amounts of reactants. Versus that word actual yield, and this is what you really go and do. It's the amount of product actually formed or recovered when the reaction is carried out in the lab. Now, for the problems that we're going to be doing, the actual yield has to be given to you in the problem. Theoretical yield, technically you've been doing that all along. Anytime you do a stoichiometry problem for me, that's the perfect reaction. That's your theoretical yield. Actual yield, like I said, either you have to go do the lab or it has to be told to you in the problem. So let's look at this one. It says a chemist was supposed to produce 75 grams of aspirin. However, he squandered some of the reactants for his own personal use, although he was later fired for this. So only actually made 50 grams. What was his percent yield? So actual yield, 50 grams, divided by theoretical yield, what he should have made, times 100. And you find out 66.7%. If we go ahead and look at this one says, what is the percent yield if 5.5 grams of hydrogen reacted with nitrogen to form 20.4 grams of ammonia? This is what we're producing right here. We're yielding that amount. That's our actual. But again, I don't know the theoretical amount. So what I have to do is I have to do a stoichiometry problem. I have to figure out how much ammonia I should have formed. So, just like you've been doing, we have to balance our chemical equation. We're going to start off with our given here, 5.5 grams of hydrogen. We're going to go ahead and convert that to moles. And as we convert that to moles, we're just dividing it by the molar mass of what H2 is. Our next step is going to be your mole to mole ratio. 3 moles of H2, 2 moles of NH3. But because this is grams right here, my last step is I have to go to grams. So 17.04 grams of NH3 is 1 mole of NH3. When I run this calculation through, I find out that I should have formed 30.93 grams of ammonia, or 30.93 grams of NH3. That number from stoichiometry, that's my theoretical yield. Now, I have to go ahead and do my percent yield, actual amount that was given in the problem, divided by the theoretical amount, 30.93, multiplied by 100, and your answer, 65.96, is the percent yield. Let's do our last stoichiometry involving energy. Every chemical reaction will either absorb energy or it's going to release energy during that reaction. If energy is endothermic, or if it's on the reactant side, you're going to find out that you have a positive value, a positive energy value, positive answer. If energy is exothermic, or is on the product side, you're going to find out that your number, or that your answer is going to end up being a negative energy, or a negative value. Your steps for mass to energy: number 1, balance the chemical equation, as always. Number 2, convert that mass to moles. Number 3, instead of mole to mole ratio, this one's going to be your mole to energy ratio. Again, it still comes from the balanced chemical equation. Number 4, solve the problem. And finally, number 5, apply that correct sign for energy. Like I said, if it's on the reactant side, it's going to be positive. If it's on the product side, you're going to end up being negative. Let's look at this example problem. We have 2 NaHCO3 plus 35 kilojoules of energy will produce sodium carbonate plus carbon dioxide plus water. The question says, how much energy would be required to decompose 3 grams of sodium hydrogen carbonate? So again, we start off with our given, 3 grams of the sodium hydrogen carbonate. Next step is we have to convert it to moles. Add up what NaHCO3 is, and you get 72.01 grams. That's 1 mole. Our last and final step is use that mole to energy ratio. Again, this comes from the balanced chemical equation. If you look here, I've got a coefficient of 2. Next thing is, in that equation, I have 35 kilojoules. So, again, NaHCO3 is going to go on the bottom, so I'm going to put 2 moles down here. The energy is going to go on top. When you run this through, 3 multiplied by 1 multiplied by 35 divided by 72.01 divided by 2, you get an answer of positive 0.73 kilojoules. Okay, positive 0.73 kilojoules. Positive because notice it's on the reactant side. This one's going backwards. This is the one that's going to be in your Google form. If you notice here, I'm starting off with the 427 kilojoules, and I want you to tell me how much oxygen did we use to produce that much energy.